Hello, Internet. Welcome to episode 60 of the Stanford MLSys seminar series. My name is Dan. Today I have with me Fyodor,
Hello.
Piero,
Hello.
and our guests, Igor Markov and Norm Zhao. So today we're going to be talking to Igor about Looper, which is an end-to-end ML platform for product decisions. As always, we're going to have a half-hour talk followed by a half-hour podcast-style Q&A. Throughout that whole thing, feel free to post questions in the YouTube chat, and we'll aggregate them and ask them to Igor during the Q&A. So just a little bit about Igor before we get started. So Igor is a research scientist at Meta. He was previously a EECS professor at the University of Michigan. He received his PhD from UCLA. He's an IEEE fellow and ACM distinguished scientist. He researches computers that make computers. He's written 5 books, 4 U.S. patents, and over 200 publications, which have been published, in some of the best conferences in the field. So we're very excited to have him on today. And with that, Igor, take it away.
All right. Thank you, Dan. In this presentation, I will introduce an ML platform that we developed at Meta. This platform hosts hundreds of ML models and produces millions of AI outputs per second. This platform is used by product engineers and emphasizes end-to-end coverage of the ML development cycle. It encapsulates a number of MLOps functionalities and supports product impact measurement and optimization. And of course, if you want to read more about this platform, there's an archive paper that will be updated soon. Now, the platform is called Looper, and it supports the notion of a smart strategy, which is a way to embed AI capabilities into a software system while keeping ML code separate from application code. A smart strategy produces AI outputs, decisions, predictions, based on well-defined data and label sources using a hosted ML model and a decision policy. Here, a decision is not necessarily a binary decision, but can be, for example, content ranking or an entire configuration of a video codec. We support some reinforcement learning applications, and in this case, the decision shape is the action space. Smart strategies are deployed in products interacting with many users in the environment. And closed form policies for such cases are usually suboptimal. So you have to learn from data, and this motivates machine learning approaches. There are many examples. They include application settings and preferences for many products. They include adaptive interfaces, where some options are shown only to users who are likely to be interested. This is important when screen space is limited. In the presence of ads, controlling the frequency of ads, or even just user notifications is important and can be addressed through smart strategies. I will talk a little bit about prefetching and precomputation that reduces latency, but needs to be careful about bandwidth utilization. And I'll also discuss applications to content ranking and more generally prioritizing available data or actions. Among the challenges addressed by our platform, let me emphasize the first 4. The colors here are mostly just to make the slide more interesting. They don't have much meaning. The first 4 are essentially related to optimization or product objectives, and also how the data changes in time, how you can evaluate the performance. So it turns out that product objectives, especially delayed or long-term objectives, they rarely match closed form loss functions used in machine learning. So you have to use proxies, and they're not exact. Also, product-generated data tends to drift away from training data. And this motivates retraining of the model and brings a number of MLOps issues. The basic idea of using ML is essentially capturing some correlations in data, but that does not imply that when you embed ML solutions into products, that the product metrics improve. So the gap between correlation and causation is important, and this is why you have to use causal experiments and A/B tests. When doing this, we also can handle personalized treatments, as I will explain in the talk. The next three challenges look more mundane, but are very important in practice. In particular, we were surprised that real-time feature extraction can be a bottleneck, consuming greater resources than training and even model inference. Now, this busy figure from our paper, this is figure 1 in our paper, compares horizontal ML platforms, which are essentially toolboxes, to vertical or end-to-end models that capture the entire machine learning development flow, from data collection to product impact evaluation at the bottom. The flowchart also compares specialized vertical platforms on the left to general purpose platforms on the right. Specialized platforms focus on one application or product surface area and usually have greater data capacity. General purpose platforms employ more pervasive automation. In this work, key contributions include platform design principles and the implementation of the platform called Looper. This platform is internal to Meta and is used by product engineers. It targets ease of use and rapid development of models of moderate complexity for moderate data sizes. But we are extending the infrastructure and the platform to larger data sizes. There isn't really anything inherently limiting in the model, in the platform, but the implementation, of course, needs to be more powerful to handle larger data volumes. To use Looper, no ML coding or expertise is required, in line with the ideas behind declarative AI. But at the same time, ML experts, they tend to like the automation on our platform. Even when they can do something, if it's done for them, that's good. Looper extends the notion of end-to-end or full stack platforms from data collection to evaluating and optimizing product impact via causal experiments, in practice A/B tests. And here we consider personalization and something called heterogenous treatment effects. Heterogeneous treatment effects, roughly speaking, can be illustrated. Let's say you evaluate a new medication for, let's say, hypertension. It can help some people, and other people may get worse with it. So predicting who will benefit from the treatment is important. Now, the technical highlights you'll see in the next 10, 15 minutes, I'll skip that. To support smart strategies with machine learning, one tries to approximate product goals by ML loss functions and decision policies that process the predictions of the models. The choice of machine learning model can make a big difference, obviously. And we've seen some simpler models consistently outperform more advanced models, which is very familiar to Kaggle contestants. GBDTs and XGBoost do consistently well in those cases. Applications deployed on our platform do not include images, sound, or difficult NLP tasks. Instead, we deal with tabular data or metadata. No pun intended with my employer. Now, in the category of ML ops, we acknowledge the importance of logging and monitoring ML performance. It allows to catch problems as they arise. But Looper also optimizes resource usage, and we've had a couple of projects running for the last year in the group. Now, I'll talk about those a little later, but on the right, you see that among several tasks supported in our platform, such as reinforcement learning, multitask models, contextual bandit regression, still binary classification dominates. It's simple, it's easy to use, easy to evaluate, the turnaround time is faster, so why not use it? And in the little insert in the figure, you see the different types of models, even though we have sparse NNs, but GBDTs, specifically XGBoost, tend to dominate, and our platform chooses which model type is better for a given application. So that's not just someone's whim. But for some sparse features and categorical features, in some cases, sparse NNs do better. Our platform philosophy, and that will lead to design principles, acknowledges the scope of our applications. As I mentioned, we don't do image processing. The platform is geared towards managing mixes of categorical, sparse, and dense features that are not related, maybe not correlated with each other like pixels are in an image. And we have ML models that tend to be lightweight, deployed quickly in large numbers. But of course, if you want to work with reinforcement learning, that tends to be heavier. Now, data trends may change quickly. So if you're used to Kaggle competitions or research activities where you have a data set that is well defined, we live in a different world. Things can change daily or weekly. And so regular training of models is important, and deployment of models is automatic, which requires some care, right? And as a result, compared to other models, other platforms that we've seen at Meta and elsewhere, our platform has very fresh models. It reflects data trends very well. Now, this platform is intended for company engineers. So of course, we want fast onboarding, robust deployment, low-level maintenance, but we also have access to the metrics store, a lot of data in our company that wouldn't be easily available outside. And so we leverage this data. And one other point is that the end-to-endness of our platform allows us to account for resource usage in a very comprehensive way. This includes data joins, feature extraction, and the subsequent evaluation with causal experiments. With other platforms, things just fall through the cracks in terms of resource accounting. Now, when we think of our platform, we focus on workflows. And it's a vertical platform, obviously, so that's why we have the visibility of the workflows. It's not a toolbox like horizontal platforms that we use. And so these workflows tend to include laborious and repetitive maintenance operations that engineers like to learn, but then not do repetitively. And we automate those. That's part of the value of the platform. There are some operations that are difficult to reason about, especially tuning to product metrics. If you think of, say, monthly active users, well, it's not clear how a particular product contributes to monthly active users. There could be all sorts of nonlinear effects, but our platform automates all these things. The platform design concepts that we use to reason about the platform include the application context, which is roughly the data that is available to produce AI outputs. Then product metrics. It's pretty clear what they are, but they're often noisy or delayed in time, or both. And to use ML, we need proxy ML tasks that model or approximate the product metrics. And of course, the overall performance is evaluated by causal experiments and live data. That's a big deal, and that's where some of the platform extensions are very useful. Unlike traditional ML integration that is based on data files, we pursue software-centric ML integration. Here, the platform keeps the full chain of custody of the data. The client of the platform doesn't need to worry too much about files or tables. The tables are maintained by the platform. And so the platform client embeds Looper RPC API to intercept decision points in the application code. And this keeps application code separate from the ML code. Data handling is abstracted away and delegates quality issues to the platform. This makes it easier to reason about training. In our online-first approach, we log features, later observe labels, and join them in real time. And this helps avoid data leakage, discrepancies, and other data hygiene issues. Now, to illustrate some of these principles and introduce new ones, and of course the architecture, let's walk through this flowchart and keep in mind a use case where we need to rank several content items. You can think of newsfeed ranking. We don't use this platform for newsfeed ranking, but it's a good example. You can also think of notification ranking. And so the client API on the left contains two RPC calls, get decision and observe. Get decision logs the inputs for ranking, for example, taken from the feature store, that's arrow number 3, and tries to produce an output, a ranking, if an ML model is present. If there is no ML model yet, hasn't been trained yet, then the prediction is just null. But the invocation logs the inputs, and these inputs can be used for training. A little later, the observe RPC call collects feedback, which, for example, which items were selected. It's not a full ranking, but it allows us to evaluate some loss function. And then inputs are the combined data rows are sent for training. So that's the arrow number 6, and the ML model is trained. That's arrow number 7. The new model is published as a canary or a shadow model that is evaluated on live data, but does not affect the product. It is published to the predictor for live inference. That's arrow number 8. If the canary outperforms the prior model on live data, it is promoted in the config system. That's arrow number 10. And the entire configuration is maintained in the strategy blueprint, number 2, which will be covered next. The strategy blueprint ensures the ML configuration is separate from code and also ensures that everything that needs to be configured can be versioned. The blueprints support full versioning for the entire strategy deployment. That includes feature inputs and features, labels, the model, and the decision policy. It captures data compatibility. For example, if you update or change the version of one of the inputs, then the entire version increases. And this supports vertical optimizations for product impact. In other words, if you run several experiments and one of them comes out first or best in quality, then you at least have the full configuration. You could figure out what to do next. In this flowchart, the large rectangle in the upper right represents a blueprint with 4 components. There's version 2 at the front, but then there's version 1 at the back. And as in the looper flowchart before, the product code invokes the API that's on the lower left. And these calls invoke directly or indirectly a particular version of the strategy blueprint that specifies which training table to use, which hyperparameters values to use, and other details. When an ML model is trained, it is canaried and can be used for A/B testing. These causal experiments are driven by the experimentation system on the left side. And the system uses blueprints for bookkeeping. Adaptive experimentation uses Bayesian optimization to perform vertical optimizations for product impact. By vertical, I mean modifying hyperparameters, data sources, weights in the decision policy, potentially label sources, and so on. Okay. Now that we covered the core architecture, I wanted to say a few words about specializations. And here I'll mention 2. One is for ranking, where the shape of the decision is a ranked list. And the other one is for personalized experimentation in the form of A/B testing. For ranking, there's definitely better support for ranking objectives that account for positional bias or the trend where people tend to select the first or the second items. And the API is just more detailed. So that's one way to specialize the platform. Now, for integrated experiment optimization, a big deal is the detection of heterogeneous treatment effects. Here, as I will explain a bit later, the platform can build a model automatically that predicts which subjects of A/B testing are going to benefit from a particular treatment. And this by itself is a form of personalization because you use the available data. And then, of course, when you do A/B testing, you have to account for personalized treatments, right? It gets a little complicated. And it's a deep topic that is, far beyond the talk today. We have separate talks on this in our group. Now, the optimization of product impact uses Bayesian optimization, mostly because Bayesian optimization is really good at using very few attempts. You evaluate the product impact several times, then Bayesian optimization suggests what else you should try. You try that, do this several times, and you converge to pretty good configurations. All right, now, so let's talk about applications. And the second application will deal with personalized experimentation. Now, the first one is really 2 examples, where one example was built by a partner team within Meta, the GraphQL team, and the other one was built by our team on top of the core platform. The idea is that when you prefetch data, this can improve latency and data prefetching can be thought of broadly, either multiple subsystems on a server that talk to each other, or perhaps a client on the smartphone and a server, right? So when you prefetch data, such as images, it improves latency when these images are actually needed, but it takes more bandwidth. And if you prefetch everything, then you'll just use up a lot of bandwidth for perhaps not much benefit. So in the first example, Meta's GraphQL decides, GraphQL is a protocol for data communication in a structured way. It decides which prefetch requests to service and which to skip. And this saves client bandwidth and server-side resources. In practice, this provided a 2% compute savings at peak server load in a system that has been very highly tuned before. In the second example, this is a distributed example with predictive screen rendering by Meta's or Facebook app client on lower-end devices where resource limitations are tighter. And so it turns out that in order to predict what to prefetch and what not, what to render, what not, it really helps to model information about users via embeddings based on the history of what they did before. This extracts information in just the right way. Okay. Let's see. The next application example is a personalized experimentation. And here, I wanted to kind of continue this idea of labels that are available for free, because when you prefetch something, very soon you know if in the next 2 minutes this data was used, right? So in personalized experimentation, you also get labels for free because A/B testing produces labels for you. And if you think of A/B testing, as something that you want to predict, right? Then you have a number of features. You don't necessarily know what's important, but you could try to predict the results of A/B testing, right? And so the Looper API for personalized experimentation plugs into the A/B testing API and collects a supervision in the form of these labels, as well as various features. But then we have to be careful with feature selection, not to have thousands of things we know about subject of A/B testing that might not even be relevant. Okay, now this is all integrated into an experiment optimization system that cares deeply about heterogeneous treatment effects, which subjects of A/B testing are likely to benefit from treatment. And it turns out that many such experiments are done kind of manually. It's not a new idea to do this experiment, but automation is very powerful. It simplifies the learning curve and makes the client code much simpler because the decision API, in this case, is very similar to the standard A/B testing API, and they connect. Our platform handles data sets automatically, as I described before, but now this is in the context of A/B testing. And so models are created automatically. The client of the platform doesn't need to worry about even configuring the model, although it's possible to change the configuration. Now, the impact of a smart strategy can be directly compared to baseline. And you can embed the smart strategy into the experimentation framework just fine. That's part of the API. And it's very important that this is an internal platform to Meta because we have the access to metrics and to the trade-offs. So we use multi-objective optimization where we could create a balance of different objectives without pushing any one of them too far. The adoption of our platform has been quite broad. I should update the 70 figure. It's really 90 plus product teams. At any point in time, the platform hosts 400 to 1,000 ML models, and it makes 4 to 6 million predictions or decisions per second. These we call them AI outputs. Could be a lot of different things. The application categories can be formulated as personalized experience, different types of ranking, but not feed ranking, prefetching of data and precomputation, user notifications and prompts, and then value estimation, basically numerical predictions such as latency or memory usage of a data query. And all of these are implemented without really changing the application code too much, with ML code being in our platform. Typically, when smart strategies are adopted at Facebook or Instagram, the product teams don't require additional staffing. We have pretty good documentation, and some help is usually provided. We answer questions. but it's generally a self-serve platform, and it's been successful in this form. It is common for product teams to improve their product goal metrics that they declared for a calendar period by 20 or 40% of their total improvement due to Looper. So Looper contributes to 20 to 40% improvement of what they managed to do during the calendar period. In some cases, the teams outperform their goals by 2x. I mentioned that we care deeply about resources on the Looper platform, and here's some profiling data. First of all, I have to say that the model selection, the automatic model selection, whether you use deep networks or GBDTs or something else, this is done automatically by the platform, although you can, of course, always supersede the choice. And in many cases, it's GBDTs, which are quite light. They're fast to train, their inference is fast. And so let's look at this figure 5 from our paper. You see the different colors, but you should really look at the light blue color, feature extraction. It clearly dominates in the important cases. And so because GBDTs are so light, or XGBoost is so light, it turns out that feature extraction is more time consuming than training and inference. And here feature extraction includes joining, it includes some data operations, it includes accessing some tables in real time, and that can indeed be expensive because of the network access and database access. Also, feature engineering can be very expensive. We have some engineered features that are very useful, but much more expensive than raw data. And so this platform allows us to think about the economies of scale, and we perform resource optimization that might have been too expensive or too boring for a single use case, right? We can amortize the effort over multiple use cases, right? And in particular, we optimize this feature fetching or feature extraction bottleneck to a large extent through feature selection, right? Again, another big topic that can be discussed. In trying to understand what contributed to the success of the platform and also what we might be missing, we studied the literature, and it turns out there is a great paper that lists common barriers to entry, and I think we handled those quite well. We also surveyed our adopters and asked them what helped them succeed. And so the challenges that were mentioned, and there are more, of course, but these are the top items in the survey. The first one is manual optimizing parameters in large search spaces, basically AutoML. So our platform delivers value through AutoML. Figuring out correct rules to make heuristics effective. This is important because many of the applications that we host previously were handled by heuristics. And you start with a simple promising heuristic, and then you maintain it, and you add different countries and different time zones, and it just becomes unwieldy. Another one is trading off multiple objectives, because we have multi-objective optimization on the platform. Again, people do it once or twice and then get bored. And then, of course, updating heuristic logic can become difficult, especially when people come and go, when someone designs a heuristic and then leaves the team. For others, it's usually difficult to follow the logic in the heuristic. It turns out only 15% of teams, product teams in this case, that used our platform include ML engineers. And this is why we provide value in easy to use interfaces and not asking to write ML code. So that's a big factor for adoption. But it turns out that experienced engineers did tell us that they enjoyed the platform because of the automation that is smooth. It connects through the entire ML lifecycle. And so it saves time. People can create more models instead of struggling with a small number of models. The learning curve is shown here. This is averaged over responses, but it's pretty representative in this case. It takes about 2 days to configure a model. It takes about 2 weeks or less to train the model on product feedback and maybe revise it once. Online product experiments take up to 4 weeks, and product launch happens anywhere from 1 to 2 months after the initial data collection. As mentioned in related literature on such platforms, one aspect of the value is low technical debt, because there are some teams with hero efforts that can launch something it runs, but then they have to go back and fix so many things that it's not even funny. In our case, people launch the models and they're free to go. Things just work. You just need to watch the data alerts. That's because we support recurrent training, canary model publishing, and data visualization. I already mentioned monitoring of different aspects such as ML performance, but even monitoring label and feature distributions over time sometimes catches problems early enough that you can do something, right? You get alerts on data drips. For future work, we are thinking beyond what we call the causal paradigm. In the causal paradigm, you basically have a well-defined data set, a well-defined loss function, and some time to play with data, to play with the objective, with ML models. In our case, data changes. In our case, we want to deploy things quickly, and we're not that concerned about SOTA. You know, if we're 0.5% better by some loss function, 0.5% worse or better by some loss function, we really care about the product impact, which may correlate or not with the last, 0.5% in the loss function. And so if you trust, or when you trust your platform, you can full automate iterated online experimentation. They are not far from that. It's mostly automated, where you perform an A/B test and then you tune parameters and then another A/B test. Now, full automating feature engineering is harder. Feature selection with significant efforts can be largely automated, but yeah, feature engineering, that's a tough one, especially for complicated features. In the examples that I've shown for prefetching and for PECs, the supervision, the labels essentially were automated. The result of A/B tests gives you labels, or for prefetching, whether or not the data was actually used 1 minute later gives you labels. But we think this can be generalized. And so you could select the label stream, maybe out of several available, and that's similar to feature selection. And then, of course, now that we automated resource optimization, the next step would be to automate the trade-offs between quality and resources, right? In an end-to-end ML platform, you would expect that to be available. Now, looking further into the future, we see that we have a lot of models deployed, a lot of use cases, and we view them as independent largely, which means linear accounting for resources. So many of these use cases are actually connected. A simple example, if there are limited resources on the platform, maybe limited predictor resources or limited total CPU effort available, then you have to tone down something, and that's a nonlinear effect. Also, use cases that interact through product surfaces have nonlinear interactions, and then there are, of course, network effects where a friend of a friend may see something and do something, and these things would be very hard to reason about without automation. Now, to summarize, I explained how smart strategies enrich modern software. They learn from data when closed form policies are not good enough. And we developed support for a vertical ML platform that is accessible to product engineers at Meta, even when they don't have ML expertise. We evaluate the results and the impact by product metrics, not just abstract loss functions for ML models. And we extend the notion of an end-to-end vertical platform to go from data collection to optimizing product impact. Specifically, the online first approach to data collection tells the platform figures out what data to collect, and the platform maintains full chain of custody of data, preventing costly mistakes that clients like to make. We have a very compact RPC API, just 2 calls. It intercepts decision points in software applications. And we have extensive AutoML that optimizes full decision strategies, not just bare models, where the bookkeeping is handled by the strategy blueprint. We optimize product impact via A/B testing, and we account for personalization and heterogeneous treatment effects. Of course, the use of this platform in Facebook products or aspects of the Facebook product and Instagram has been extensive. This is all I have for today.
Well, thank you so much for that talk, Igor. So as a reminder to the YouTube audience, feel free to send in questions at any time through the live chat, and we'll convey those to Igor. I see that there's a few already, so looking forward to going over those. But just to kind of get us started, since we do have Norm here today, I was wondering if you could maybe tell us a little bit about how does a system like this come into being at a place like Meta? What's kind of the process from the get-go, like in terms of seeing a need, or what types of needs did you see, and then kind of assembling the team and kind of building it. If you could maybe just provide some color on that, since both of you are here today.
Yeah, I'd be happy to answer that question. So I was fortunate enough to be involved with this project from the beginning. Um, uh, Basically, Meta is a very bottoms-up company, and so we didn't kind of plan this as a grand strategy and then execute on it. It was very much an engineer. I was supporting EpiLearner Flow team at the time, which is kind of training-oriented system. An engineer, just seeing a lot of kind of product engineers coming to us like, I have a great idea for machine learning. Please help me build this feature. And just from telling them from how do you set up logging to getting a table and training a model, evaluating a model, putting it, hosting it somewhere, and then running it, and then getting all of that together, it's basically way beyond kind of what a single engineer can expect to be able to deliver. And so the idea was to kind of, can we package everything together where the product team really cares about product impact, right? How do we kind of just give that to them without having to worry about kind of the ML bits? And that's how it came to be. And initially, I was actually a user of the system. To give you a sense, I had an intern. I was an engineer at the time. I had an intern who came to work for the summer, and my idea was, hey, like, we run these machine learning jobs in the cluster. Wouldn't it be great if we can predict, how much machine resources they take up when we issue them, so we don't overload the cluster? And I wanted the intern to build something, and it was way too much work to do it anywhere else, basically. And through that, I became involved in the project.
Cool. Yeah, that's really interesting. I'm wondering, Igor, kind of from your perspective, I know because you were in academia for a while. What are kind of some of the differences when you're building a system in industry like this versus something you might build in academia, or kind of how do you balance that, or maybe with the desire to go chase after a shiny research question or something like that?
Yes, I think the emphasis on product impact is a big difference, and it drives many other specific implications. One example is in academia, people like to train models, big models, and they spend most of the time training models. In the industry, inference is relatively more important, right? And then having the variety of models on our platform, we are less locked into, say, deep learning, right? If XGBoost works better, we go with it, right? Although we try to improve all the models that we have, right? And I guess for people in academia, not specifically thinking of A/B testing, I think that's a fairly different world of causal effects, right? And it's not hard to imagine where a good model that produces good scores doesn't actually improve the product, right? But sort of when you see it, this can be due to network effects, due to a lot of different things, right? It could be like a feedback loop in an application, right? And so thinking about that is different. Another aspect, and this is, I guess, more general, not specific to ML. In the industry, you worry more about things that might break, right? Everything works at some point, and then you didn't notice that your data drifted, right? You didn't notice that some data source died, some feature was deprecated, and by feature I mean data feature, not product feature, although it could be both, right? So it's a different mentality, and in the paper, we try to emphasize this end-to-endness. You have to worry about everything, right? But you want to automate things so that you can you have the ability to fix anything, but you don't want to track all of these things manually as you would do when you just work with flat code.
I like to add a little bit to that, just to kind of think about like which edge of the spectrum. And one of these metrics that we haven't started measuring, but I think it's very reflective of how we think about this, is like there's one end of the spectrum where you want to do the best job you can on some machine learning task, right? And maybe at a place like Meta, you might have hundreds of people working on one very important machine learning use case, right? On the other end of the spectrum, there are you do this engineers per model or use case kind of metric, right? You might invert this and say like, are there places maybe we're thinking about like use cases per engineer that we need to do, right? And when you're thinking in that regime, a system like this makes a lot more sense.
I think, Norman, one thing here that I can completely second on this is like, if you think about the integral of the problems that are worth for the company less than one engineer's time, there's a lot of value to be untapped there, and a system like this can untap it, right? So I completely agree with that.
I wanted to jump in. Norm, you mentioned very important models and use cases. I recall hearing that most of the AI computation done at Facebook is to train these huge recommendation models, like big embedding tables that need to be constantly updated. I was wondering if that's a use case that Looper can actually support.
In theory, yes. In practice, it's very hard. And I think I can think of two reasons why it's hard. One reason is the push to get the biggest model and the most data, right, to generate the best quality for a particular use case, often entails I don't want to call shortcuts, but optimizations that assume a certain context, right? If you assume, maybe it kind of pushes you to build systems that are maybe not as modular as you like, right? You assume what the other side of some interface looks like in order to get some win in throughput or something, right? And so what that does is it kind of pushes you into a more narrow domain and a limited surface area, maybe, right? And so then that kind of, on the other side, pushes against kind of a more general vertical system that we want. It's nothing that can't be solved in practice with enough engineering power, but the other side of the limitation is, there's a fixed amount of engineer that Meta is able to hire to build all its use cases, so we have to kind of find ways to balance that as well.
Again, all of this, by the way, resonates really well with me, right? I see like a lot of overlap with the kind of work that I've been doing on Ludwig, and also overlap with the declarative machine learning systems paper. So I'm super excited to chat about this stuff. One interesting question for me, for both of you, Igor and Norm, is there are some design decisions and some assumptions that you made in the design of the system. Two of them that I find particularly interesting to discuss about are, one, the decision to think about, I don't know how I don't remember exactly how you put it, Igor, but I think was online data.
Online first.
Online first. Yeah, that was the principle. Yeah. So I'm very curious. I can see the value in that, like you were showing that you don't have any more problems with leakage of data and things like that, right? On the other hand, I'm curious about also the downsides. I can imagine that probably reproducibility of older situations may be a little bit more tricky. Curious to expand that. And also the other one was to work specifically on tabular data, right? So all these, I'm curious, like the distribution of the tasks that you were showing, if you imagine like working with other types of data, like also text cases, images, if you would expect that to change, and what are the implications that would a change like that would make in the system, right?
Yes, that's a good point. Both are good points. So in terms of, first, I guess the most generic answer I can say is that in machine learning, in the literature, often when you read a paper and you look at the results and you like them, you have to check carefully what kind of data they're using, because some papers are image processing only, right? And they make general claims. And we are very careful to say that we work with metadata. And in metadata in particular, you could have features that don't look like don't look similar at all, are not correlated, and so you have to handle them. That's a challenge, right? That's where sometimes just vanilla DNNs and CNNs don't really work well. Now, in terms of, there are issues related to joining, because you join a lot of different features coming from different sources. Again, in image processing, this doesn't really arise much, right? But in terms of design decisions, the online first, that's kind of a different part of your question. It's harder to do data cleaning. So we know that some platforms have a very extensive capability to do data cleaning, but we have a project now. My intern is working on this right now with some good results, where we actually are able to automatically clean the data, right? But you wouldn't expect a great variety of tools that the user can select, because we try to automate everything and do everything in one flow. So that's really the trade-off, right? In terms of reproducibility, I mean, all the data is safe, right? And as long as you can keep it, right? If it's not people's data that you have to at some point clean, right? Maybe in 60 days, then you do get reproducibility, right? On the other hand, if the underlying trend in data changes, then it's not even clear what reproducibility means, because your past model will not work, a month from now, perhaps not as well, at least, right? So the focus on non-stationary data trends is a big aspect of our platform.
Yeah, that makes a lot of sense. And again, when I was saying about reproducibility, it's like, also I can imagine like going back in time, auditability and things like that. But maybe that's more it's a design choice, right? So it's something that you're optimizing for something slightly different, and that's completely fair and completely, I think you made the really, really reasonable choices for the assumption that you're making, right? So
yes. We're not claiming to solve any old challenges. These are
absolutely
very applied decisions. Yeah,
makes sense.
Like, I can add a little bit more, because to add on to Igor's answer, with like use cases that we've worked with, because you mentioned about trade-offs that we've made in that design choice. There have been use cases that just weren't as good fit, and it has to do with what Igor mentioned with the dynamic data distribution changes. Like a lot of the image and whatnot use cases, the data set is fairly fixed, right? The task is fixed and the distribution doesn't change. And so they don't benefit much from our use cases. So some users, they're okay with, I have a fixed data set, I need to train a model, and I just need to evaluate, run the model on some data offline and save the results, and I'm good, right? And those don't work as well in our system, or they don't get as much benefit from this system. With respect to like the image stuff, that's actually one of the sad points that we have in our system, that all this great literature out there, that innovations that people have is all like NLP and CV and whatnot. And so we get these papers like, cool paper, does it apply to our use case? I don't know. So
yes. Sometimes it does, sometimes it doesn't. Right.
Yeah, if you guys at Stanford, you can think about like the challenge is the data we have. It's very hard to build, benchmarks with, right? Because they're private user data of user interaction. So how do we take that challenge and or figure out a way to kind of get academia involved in that? Would be great.
That's very interesting. And by the way, I understand that the design choices one makes in the system that impact and make it more or less useful, actually more or less added value for specific use cases. It makes a little sense. I still believe that there is going in the direction of something as generic and general as you were describing could also include additional tasks, and I'm excited to look at the future, because I'm sure that you're also already thinking about it for the future too.
Absolutely.
I see that there's a question from Kinbert Cho in Zoom.
Yeah, so we'll actually wait for the private for that. But that's actually a great transition. There were a couple of questions that came in from the YouTube chat, so I wanted to highlight a couple of those. So Anand Raj on YouTube asks, can you? So he has a few questions. Let me maybe start with one of the potentially more fun ones. Could you please share some use cases from the metaverse experience?
I believe there was a ranking use case that people tried. I don't know if they shipped or not. Yeah.
I can outline kind of the reasoning why this is important for the metaverse, because if you're wearing a device on your head, right? If you're not looking at a big screen, then screen space is limited. Your inputs, you don't have a keyboard, right? So prioritizing the actions, I mean the menus and what is shown to you, that's super important. And it turns out that we have use cases like this, not only for the metaverse, but this principle of limited screen space and limited communication bandwidth. It emphasizes the need to prioritize, right? Based on some available features that you don't want to spend too much time thinking about.
Gotcha.
Yeah,
All
if
right.
they use GraphQL to prefetch data, maybe they automatically get something.
All right. That's more content than I was expecting for that answer. So he had a couple other questions. So are there any use cases for kind of physical industrial settings like a manufacturing factory or things like that? And he had another question: what type of infrastructure, I think like hardware infrastructure, does Looper run on within Meta?
All right, so on hardware, I don't believe we have any, but I think it's mostly a matter of kind of marketing, which is a whole different discussion. How do we market something like this, right? There are answers, but I think we can probably do better. Now that the platform is very kind of trustworthy and stable, we are planning to advertise it more broadly within the company. Yeah, Norm, what do you want to say about server infrastructure?
I was gonna bring up use cases because we have like these large categories of use cases, and then I have like the off-the-wall use cases that I love to talk about that people use the system for, right? So I have three, an example. Connecting to manufacturing. So one of the first use cases of the system was from production engineering, which when a machine goes down in a data center, technicians gotta go in and do something, right? And so they built a system, built a model on the system to kind of suggest to the technician what that something that they need to do might be to fix the machine. Whether it's to swap the hard drive or reboot the machine or something. So that was maybe that connects to manufacturing. The other two are interesting ones. We have internal applications where we try to book a room, and you can't get a meeting room because it's not. This is before pandemic times, and somebody, a creative engineer decided, hey, I'm gonna build a model to tell you your chance of getting that room if you put yourself on the wait list. So that's actually an application that exists in our calendar app internally. So it enables a lot of creative things. So we joke about, like, internally we have a code word game that somebody in our team should just build a predictor or to tell you what which team's likelihood of winning the game when you progress to a certain point.
That's actually super fascinating because I think lowering the barrier of entry for product teams also increases the potential for creativity in the users, right? So that's super fascinating.
Yeah, definitely.
Yeah, but as far as the question about hardware goes, I think so you remember that GPTs or XGBoost dominate the usage, and for those you don't need specialized hardware. So some pretty common servers at Meta are used for this, and the latest version of the paper that will be updated soon will have some numbers of how many servers are needed. For DNNs, for inference, I don't think we use any specialized hardware. For training, we can, it's possible, but when specialized hardware is limited, the GPUs are limited. Sometimes the wait in line to get access to the GPU is longer than training on a CPU. So you have to kind of be careful.
Gotcha. And one more question from the audience. So Ajoy Kumar is wondering, how do you scale out the inference services to get to 7 APIs a second throughput? And he's also wondering, is the system similar to platforms like Michelangelo or other systems that we've seen people write about in arXiv?
So we definitely see some similarities, and our paper does cite many prior systems, and there are some comparisons. We also, so this newer version that will be updated soon, it does go deeper into what's really new on our platform and what we've seen before. Of course, many industry platforms are not fully documented in open literature, so these are mostly guesses as to novelty. But overall, the architecture is I think pretty interesting. In terms of how you scale, what was the question? Was it about inference time or the API?
Yeah, how do you scale out the inference services to get to the throughput that you need?
Yes. So in our case, the simple answer is you profile, you see which steps take longer, and you just optimize what you can, right? And also using a simpler model helps a lot, because for DNNs, like comparing the inference latencies in milliseconds, you get several x longer latency for inference for DNNs. But the architecture also is pretty slim, I would say. I mean, we covered everything in one picture, and we went over the entire picture in 3 minutes, right? So I've seen some systems that were over-designed, and so over-design is very expensive in terms of inference latency.
Gotcha. Cool.
I wanted. We have really great infra teams at Facebook. That's how we scale to really large QPS.
Nice. Cool. So we're slightly over time, but I just wanted to kind of take a step back and ask kind of, if you want to project forward like 5-10 years, kind of what is next for these types of systems and the types of things that we might see in industry. If you can, put on your speculative hat a little bit and kind of look forward a bit for us, what do you think is coming next down the pipeline?
We have a few things that we're hoping to get done soon. So one, let me maybe just expand a little bit on the slide that I had for future work. And so this idea of automation that understands multiple use cases and how they interact. It's a little bit mysterious. It hasn't really been done before, as far as I saw, but it's because there weren't many platforms that host so many things. Specialized platforms that just kind of focus on one thing or a couple of things and beat up on them. But there are some easy things that can be done. For example, if you have two models that serve similar results and similar data, well, can you merge them? Maybe they're not exactly the same, but you can reuse them, and it saves a lot of resources. You can also inspect, successful models, and for example, you know that some feature was useful for a model that was added a month ago, and then there was a model that was added a year ago. Before that cool feature was available, you could sort of guess that this feature might be recommended and might improve the older model. And so these are pretty much easy pickings, low-hanging fruit. So we think this can be done. But handling the nonlinear interactions between use cases, that's a big one.
Igor, did you want to cover your multi-scale AutoML idea?
Oh, yeah. So the way we think about AutoML is, there are conventional topics in AutoML where people do network architecture search, feature selection, hyperparameter tuning, things of that nature. So we think of this as kind of the first scale, the immediate scale of AutoML. Then in a vertical platform like ours, especially when you have strategy blueprints, you can optimize the configuration of many things at the same time, not just the model itself, right? And so that's the second scale or mid-scale of AutoML. And then this, handling of nonlinearity across different use cases is platform level, right? Or the larger scale of AutoML. And so that's, to us, that's the future to a large extent.
Cool. So that's a really interesting and awesome vision. So with that, I think we'll call it for the public portion of the talk today. So thanks again to Igor and Norm for coming by and giving us a talk today. We really enjoyed it. Thanks to the YouTube audience for tuning in and watching. Thanks for your questions. If you're watching online, as always, you can go to our website, mlsys.stanford.edu, to find our schedule and find our mailing list and subscribe to our mailing list. We send out something like 1 or 2 emails a week, so we promise no spam. Remember to subscribe to the YouTube channel itself and hit the bell icon to get notified when we go live. Next week, we'll be back with Cushion Rong. So she just recently graduated from Stanford and is going to be a professor at Georgia Tech in the fall. So we're very excited to have her on. With that, we'll wave goodbye to YouTube. Bye, YouTube.